Hi everybody, Eric here with another video for you. Today I'm going to go over potential due to point charges. This is in the Giancoli book. I think it's chapter 23. Um, and there's a few nuances to potential that's different than electric fields and electric force. So let's talk about it. So the equation for the potential, which is represented by V, sometimes they call it voltage, is going to be KQ over R. So it's not over R squared. And so that makes it completely different than electric field. This U term is going to be the potential energy. The potential energy is equal to KQ over R. So there's two Q's. And something I like to talk about with potential is what it actually represents. So the way I think about it is in physical terms, if you have the potential is analogous to a height. Um, so if you have like something, let's say at sea level, so let's say you have a mass at sea level. So the height here is 0. And then you have another mass at some height, let's say 100 meters higher. So at this point, h is equal to 0. At this point, h is equal to 100. And you have a mass at both spots, right? There's something fundamentally going on that gives this mass what we call the potential energy, and this mass no potential energy. And it's this height difference. So like a potential needs this is analogous to the electric potential, where it needs a difference between one point and another before you can calculate this voltage. So like a more spelt out equation would be VAB is equal to the voltage at B minus the voltage at A, where this height 0 would be similar to a voltage at B. And then this height A would be similar to, well, okay, I did it backwards. This height 100 would be similar to a voltage at B, and this height 0 would be similar to a voltage at A. And the way that the book phrases it is that they say that a charge is initially at infinity. So, or at a point at infinity, the potential is 0. So if this R is set to infinity, you can see that if you put an infinity down in this R, it would make your potential go to 0. So oftentimes the question will be phrased, find the potential at this point due to two charges, the potential at infinity is equal to 0. So that's kind of like them telling you that the difference is initially 0. So you don't have to calculate two different potentials. So again, just to reiterate all of that, I think of potential as the electric form of a difference in height, um, where 0 is my like bottom, and then 100 is like the other side. And then we generally, unless told otherwise, set one of these, the VA, to 0. Okay, so let's try to solve this problem that I've set up here. So we have two charges, Q1, which is 3 coulombs, and Q2, which is 6 coulombs. And I want to find the potential at position 5, 4 due to these two charges. And again, implicitly, the potential at A is set to 0. So all I have to do is plug in the potential due to charge 1 plus the potential due to charge 2, and that's going to be equal to my potential at 0.54. So I'm just going to call that my potential. And then you'll notice that I'm not drawing vector lines here, and that's because the potential is not a vector. It's a scalar. So it doesn't care about direction. It does care about the sign of the charge, but in this case, both charges are positive. So I'm not going to plug in anything weird into the charge sign. But all it cares about is this actual distance between here and here, or between here and here. So when I write my potential equation, I'm just going to get K, let's write it out as, my K is going to be equal to 9 times 10 to the ninth. My Q1 is going to be 3, so times 3 over my distance. If this is Q1, my distance is 5, plus 9 times 10 to the ninth times 6 over this distance from here to here, which is 4. So that's going to be equal to, let's find out, 9 times 10 to the ninth times 3 divided by 5, 5.4 times 10 to the ninth, plus 9 times 10 to the ninth times 6 divided by 4, 1.35 times 10 to the 10th, is going to be equal to 1.89 times 10 to the 10th. And this is in volts. So this is a big number. There's a reason they usually make this microcoulombs or nanocoulombs even, and then the distances are usually in centimeters. It helps out with getting this times 10 to the 10th a little lower. Anyway, the next question is usually if a charge is taken from infinity to this point, what is the potential energy or what is the work required to get a charge from infinity to this point? And generally they choose a charge like a proton. It's a little misleading to get the work right because if it is truly a proton, you would have to calculate the Newtonian force times the mass and acceleration, or the change in kinetic energy to get it from here to here. Would you have to do that? I have to think about that. Actually, no, I don't think you would. But anyway, you would just take the charge that they give you. So the charge of a proton is 1.6 times 10 to the I don't have a book. Let me just look it up real quick. Or we can do it on here. More tools. Wolfram Alpha. Charge. It's early in the morning. Don't have all these numbers ready to go. Charge of proton is 1.6 times 10 to the negative 19. I wanted to get that right. You would take 1.6 times 10 to the negative 19 and plug it into this equation because the change in potential energy is going to give you the work done. So if I take my charge from infinity, my first potential energy, again, I'm going to plug in 0 to this R, and my initial potential energy is going to be 0. And then taking it all the way to this point, I would just take the voltage at this point, multiply it by the charge, and I'll get my change in potential energy, which is also my work. So I'm going to just multiply this number by 1.6 times 10 to the negative 19, so 1.89 times 10 to the 10th times 1.6 times 10 to the negative 19. The work is going to be equal to 3.02 times 10 to the negative 9 joules. Work is in joules, so is energy. Anyway, that's my quick rundown of how to do a potential electric potential due to point charge problem, a couple of facts about it, and then that's my quick rundown of a typical problem with the work done. All right, so hope you guys are staying safe out there. Happy Monday, and see you later.